Hi, my name's Tariq. I'm the Chief Architect at Codasip, and I'm the architect of the A730, which is the world's first commercially available Cherry application core. And I'm going to tell you about how we handle tagged memory efficiently in the system without reducing the performance. So let's start with the A730 CPU, which comes with Cherry. Now what we're trying to do is connect this to the rest of the chip, but also to the DDR memory. So let's draw the DDR memory. This is the endpoint. So this is off chip, and obviously all DDR memory must have a DDR controller to talk to it. So the point is that the bus interface on the A730 doesn't just have data anymore. It also has tag bits. So it has data plus the Cherry tag bit. So the Cherry tag bit tells you whether any Cherry capabilities or Cherry pointers are valid for memory dereferencing. So whether I can load or store via a pointer or not is completely controlled by whether this hardware managed tag bit is set. And it is atomically part of this data. It cannot be separated from it. So it must be stored in memory throughout the system, so that all Cherry CPUs can see and manipulate memory tags. And when accessing the data, we must also access the tag atomically. So obviously this is part of a much bigger chip. So let's see, so there'll be different levels of caches. So let's have an L2 or an L3 cache, which would obviously be different levels, but I'll just draw them as one for now. So this cache must also contain tags, one for every 128 bits you have of data memory, you have a tag bit. And the same is true of the caches in the core. The data cache is also extended with one tag bit for every 128 bits of memory. So these tags are maintained. So by the time we get to the DRAM, so DRAMs can be in multiples of 128 bits, they can't be in multiples of 129. So what actually happens is we reserve a region of the DDR memory to store the tag bits. So all the tag bits will go into one place, and then the rest of the memory is used for data. So at some point we need to split these transactions into data plus tag. So to get to the DDR, we have to go through the NOC on the chip, which could have many other masters in. Some of them may be Cherry, some of them may not. So you could have another CPU, or you could have a GPU, or you could have a DMA engine, this kind of thing. So these would all go into the NOC. And then, before we get to the DDR controller, what we need to do is handle this tag. So the simple thing to do, let me draw this on. So we have something which is called, in the literature, it's called a tag cache. Let me do that in orange because it's tag related. So the idea here is you're making a request to the tag cache with data plus the tag. And then the tag cache is handling the tagged memory. So there are various aspects to consider when looking at the handling of the tag memory. The first thing is tags are only 1 bit, and you can't read or write a single bit to DDR memory. So we must do either a read, modify, write sequence. So if we're trying to set or clear a tag, then we need to fetch at least a byte from the DDR, which is extremely inefficient for DDR memory, as it's designed for streaming large quantities of data. Set or clear 1 bit and then write it back. Very inefficient, but that would work. And we can do that. Big reason not to do that is because we're trying to write data to the DDR, and suddenly we have to make 3 transactions instead of 1. We've got to fetch the byte, the tag byte from the DDR, we've got to update it, and then we've got to write it back, and we've got to write the data. So that's for if we're storing to memory. If we're loading from memory, then we need to do two loads. We need to do a load from the DDR to get the data, but we also have to do a load from the tag region to get the tag. And then we have to recombine those and then return them back along the bus. This is because the data and the tag together are single copy atomic, which is very important. It means it must not be possible for any master in the system or slave to see the data without the correct tag, or the tag without the correct data. The two must always be visible together, even though we're storing them separately in the memory. And this can be a little bit complex to get right. So, step one is we don't want performance loss. That's a big no-no. So we want to filter out most of these accesses to the tag region in the DDR by caching the tag bits. Caching the tag bits has several advantages. Firstly, we can store single bits without having to go all the way to the DDR memory, so we can make it much more efficient. So if we're doing a store, then we can update the store just in the cache, the tag cache. Then we go to memory, load the data, come back, and on the response, we've already updated the tag cache. So any more accesses to the same address will see the correct data and tag together. And if we're doing a load, then we send the load out, the load will go to the DDR, and then we also reattach the tag value from the tag cache. So we keep them together. But what about the size of the memory? The DDR memory. DDR memory is huge, okay? The tag cache is not going to be huge. So we can't make the tag cache big enough to cache all the tags from this region in the DDR memory. So we make use of a spatial property where we say that if this is all of memory, we know that, and these are the distribution of tags in memory. So we know that large regions of memory will never have any tag set in them. So the tag cache has a clever policy to identify regions which have no tags in them. So these three regions here, when accesses get to the tag cache knows there are no tags. And assuming that it's not trying to store a tag to one of those regions will remain with no tags, and then there's no more work to do. It just accesses the data from the DDR, and the tags don't come into it. If there's an access to one of these regions which do have tags, then the tag cache does have to do the extra work to store the tags locally, and in the case of it filling, it will have to evict and send tags out to the tag region in the DDR. But we find that this caching strategy should reduce the amount of DDR traffic required by the tags by about 95%. So there should be minimal overhead. And that's it. Thank you.